Okay. Okay. So our project was traffic volume predictor project, and the main thing we're trying to do here is to find the traffic volume for our data, which includes three junctions. And what we're wanting to do is to be able to predict volumes at 2 a.m., 6 a.m., 3 p.m., 7 p.m., and then also add a new data to a CVS file. But before we can do all that, we do have to do several steps to get to that part. Next. So who did what? We all were able to contribute in a way where we can work together to be able to make models for our data. We first started to do a cell-by-cell process, but we learned very quickly that that would take a lot of time and a lot of space in our notebook, in our Jupyter notebook. So we were able to determine to use a function where it will give us the best model for our data for each junction. And after we were done doing that, we were able to work together to make one function and um, one function for each regression for each junction for our um, models and also our interface.
And my role in this project was to handle the data cleaning, the exploratory data analysis, visualizations, creating correlation trends. Move to the next slide. Okay, so we go through the traffic volume differences across junctions. From our scatter graph, we can see that junction 1 and junction 3 show much traffic volume, frequently from 180 to 150 to 180, and junction 2 stays below 50 vehicles. So this visualization compares traffic across three junctions, and we can see that the difference tells us that junction plays a major role in predicting the traffic. Next slide. Then the next one is the traffic volume trends over time. I created the time series, and we can see that junction 1 shows a clear increasing trend in traffic from 2015 to 2017, and junction 2 shows lower traffic volume, but still shows a steady upward trend. And for junction 3, it shows higher irregular with large sudden spikes indicating special events or anomalies. Then this confirms that traffic depends heavily on location over time. Then for the daily traffic pattern, the scatter graph shows vehicle versus hour, and we can see that traffic is lowest around 2 to 5 a.m. Traffic increases sharply after 6 a.m. with a clear morning rise, and highest volumes occur between 3 to 7 p.m., showing a pronounced evening peak. The smooth upward and downward curve confirms that hour is the strongest predictor. Hence, the relationship is not linear. So we need like something like a polynomial regression model. Then model selection and justification. From our findings, the models that fit best were linear regression, polynomial regression, and the multivariate polynomial regression. Our year and junction show overall upward or grouped trends. The time series shows a pattern which is linear. Then for the polynomial regression, the formula y equals to ax squared plus bx, it shows a classic quadratic pattern. Then lastly, the polynomial regression. Traffic depends on multiple variables, junction, hour, and month. Hence, it captures the interactions. Okay.
So my main role in this project was developing the models for each of the junctions. So our first model that we'll look at was our linear regression model. And so we used a linear regression function to plot a straight line of the best fit through the data points using the form of y equals ax plus b, where a is our slope and b is our y-intercept. Looking at the picture, you can kind of see how it plotted that line of best fit through the graph. And you can also tell that that's not a very good fit for such a complicated data set. Our found RSME values for each of the junctions. For junction 1, it was about 21, for 2, about 7, and for junction 3, about 9.5. So while it shows that for junction 2, it might not actually be too bad, overall, the linear regression model is not the best option. Then for our second model, we went with a univariate polynomial regression system. So by univariate, that means that we are just using the hour as the only independent variable to create the function. And so we're using a second degree polynomial function, also known as a quadratic function, using the form of ax squared plus bx plus c. And you can look at the picture here and notice that there is a slight curve in the line, and that's where the quadratic equation is coming into play. But because, once again, this is a more complicated data set, it still doesn't curve too much. Um, Using this, we found RMSE values of about 21, 7, and 9.5, respectively, for the junctions. And while these values are slightly lower in the actual values, they're about the same as the linear, showing that, like before, the univariate polynomial is not the best option for this data set. Then for our final model, we chose multivariate polynomial regression. So this is very similar to the last one that we used. The only main difference is that instead of just using the hour as our only independent variable, we're now also using a month for our variable to help predict the traffic. So this kind of gives us a more realistic estimate for how the traffic will be at certain times. So this is once again a quadratic function, also in the form of ax squared plus bx plus c. And so you can look at that graph and see how it kind of has changed the overall look of it, kind of getting more averaged values for each of the hours, kind of a range of averages in a way. And so by doing that, we now got new RMSE values of 20.75, 6.7, and 9.4. So it's important to note that these definitely did go down a little bit from what we learned from the other two models, but it still isn't perfect. There is likely a much better model that could have been used for this data set, but it was outside of the scope of what we've learned so far. So, but because this had the lowest root square mean values, this is the model that we will be using for our prediction later on.
So I was responsible for doing the interface development on our PowerPoints. So the interface development's main thing was to create a module where we can predict the traffic volume at a road function junction. Since we had three, we needed to find one for each one. And what we did was we used historical data that was given to us from our data frames. Um, and it included like the month, the junction, and the time. We did use the multivariable polynomial regression, and the two main interfaces that was used were to predict traffic and to add observation or update our model. So the data inputs that were used was to, of course, load our CVS with our data frame information. We, as mentioned, use the hours, the month, the junction to predict the vehicle traffic and also to add extra information to the previous data frame. So the purpose of interface A was to predict the traffic, and we did this, of course, by using our multi-polynomial regression. For the user to be able to put the junction, the hour, and the month, we added that to our module. So that way they can just call forth the function and be able to input these variables. And the outputs would be the prediction of the vehicle's expected count and any uncertainty RMS, and if the RMS is like less confident. For the input user, they would be able to put the hour that they are wanting to know the traffic, the month, as well as the junction. And it uses the train model for that junction to predict the RMS as well. When we looked at the times for the vehicles, we did look at the January month, but we looked at 4 different times, which was 2 a.m., 6 a.m., 3 p.m., and 7 p.m. for junction 1, 2, and 3. For junction 1, for 2 a.m., we got a prediction of 21 plus or minus 29 vehicles. 6 a.m. was 35 plus or minus 21 vehicles. 3 p.m. was 47 plus or minus 21 vehicles, and 7 p.m. was 52 plus or minus 21 vehicles. For junction 2, we got for 2 a.m. 10 plus or minus 7 vehicles, 6 a.m. 11 plus or minus 7 vehicles, 3 p.m. 13 plus or minus 7 vehicles, and 7 p.m. 16 plus or minus 7 vehicles. And then junction 3, we have the 2 a.m., 6 a.m., 3 p.m., and 7 p.m. times as well, with 7 plus or minus 10 vehicles for 2 a.m., 10 plus or minus 10 vehicles for 6 a.m., 16 plus or minus 10 vehicles for 3 p.m., and 19 plus or minus 10 vehicles for 7 p.m. For interface B, the main purpose was to add real-world data and automatically retrain the model. This is for the user to input like a certain hour, month, and junctions and how many vehicles they observed. And the output would be the confirmation message saying that the observations were added to the model, updated successfully. So in the module, what we did was we called the old data frame. We created a function for the user to add the observations, and once they added the observation, it would create a new data frame, which then later would add to the original data frame to update it. So I just explained how it worked. But the system does retain all the junction models, and the RMS are recalculated for each model. But we did use just the polynomial one, so it would just be the polynomial, multivariable polynomial model, and predictions would improve as more data is added. The conclusion of our project was that we were successfully able to build a functional traffic prediction system for interface B, that the module can also predict traffic volumes and estimate uncertainties. We were also able to create 3 models to show different RMSEs, which included linear regression, polynomial, and multivariable polynomial models. The For the interface B, it can learn from new data using automated model updating, but overall the systems provide a flexible and adaptive solution for the traffic monitoring. Thank you.